The element distinctness problem tasks us with deciding whether all elements in an array are distinct. Doing so is very easy, as you can just sort all elements and compare each element with adjacent elements to check for duplicates. This takes big O of n log n time. The question is, can we design anything in a faster time? Unfortunately, the answer is no, as the lower bound on time has proven to be big omega n log n. This is an important bound as it affects different areas, such as sorting. So let's start the proof. The main claim of this proof is that there's a lower bound of n log n for finding element distinctness in an array. An easy way to think of this is to interpret all the numbers in an array of size n as a point in n-dimensional space on the n cube. So, for example, if you have an array of size 2, you can treat it as a point in 2-dimensional space. So, for ease of understanding, let's limit the size of the elements in an array to be 10. In reality, there's no cap, so the box is infinite, but it's difficult to look at an infinitely large box, so we will make do with size 10. So now, all points that lie on this line are representative of arrays that are not distinct. If you look, the two coordinates here are 5.5 and 5.5, meaning that if this were an array, it would not be a distinct array, or it would have duplicate elements in the array, which is not what we're looking for. Similarly, if you move up the line, 7.37 and 7.37, also not distinct. Move down, 2.74 and 2.74, also not distinct. So, anytime y is equal to x in two-dimensional space, the array is not distinct. That being said, all points that do not fall on the line y equals x are distinct, right? So if we do, for example, 1, 2, obviously by basic math, we know that 1 and 2 are different numbers, but if we look, it does not fall on this line, so it must be distinct. If we do, 7, 7, and 5, again, not on the line, so it must be distinct. This concept can also be applied to 3D space, of course, right? Because we're looking at any n-dimensional space. So in the case of 3D space, as long if you have x equals y, then it would not be distinct. X equals z, anything that falls on that line is not distinct, and y equals z. Any array or any point that falls on that line means that the array contains duplicates and does not only contain distinct elements. So then if we do 1, 1, 2, as you can see it falls on one of the planes, so that point must not be distinct. But if you have 1, 2, 3, it falls between planes, but not on one of the planes, so it must be distinct. The first claim of this proof is that the area in which we are operating in is a connected region. Well, what is a connected region? It's a region in which there's a path between any 2 points. However, for this proof, we'll use a convex region since it's just easier to use. A convex region is a special case connected region in which there is a straight line path between any 2 points. For example, squares and circles are convex regions. If you plot 2 points on any square and circle, there will always be a straight line path between the 2 points. However, crescents and L-shaped regions are not convex. There are points at which if you plot them and you try to draw a path between them, the straight line will cross out of the given region. So, why is this important? What does it mean? Why does it even matter? Well, in terms of a decision tree, it's just saying that all numbers in similar circumstances will be treated equally. For example, if we take two arrays, one with 1, 50, and 100, and another with 1, 51, and 100, and we put them through a tree, they will end up at the same leaf node. So 1 is less than 50, just like 1 is less than 51. 50 is less than 100, just like 51 is less than 100. We can also apply this to the graphical representation mentioned earlier. Where if we say we have 1, 2, and 4, and we have 1, 2, 3, and 4, these end up in the same region, right? 1 is less than 2, 2 is less than 4. 1 is less than 3, 3 is less than 4. So that means they end up here in the same region, and each of these different regions created by the intersecting planes can be seen as different leaf nodes, different possible leaf nodes for the points to end up at, or for the arrays to go through. The second claim of this proof is that if you have an array A, and you have a non-trivial permutation of that array B, then you should arrive at separate yes leaves in a tree. So here, non-trivial means there's a significant difference in ordering between the two. With the decision tree example, if you have 1, 50, and 100, and an array of 100, 1, 50, they will end up at different yes leaves. So here if we take 150, 100, 1 is less than 50, 50 is less than 100, so you end up at that yes leaf. Whereas with 100, 150, 100 is greater than 1, and 1 is less than 50, so you end up at a different yes leaf. And then going back to the graphical representation, you have 1, 2, 4, right? You're in this region, and this corresponds to one leaf. But if you have the region of maybe 4, 1, 2, you're in a different region, right? 1, 2, 4 permuted is 4, 1, 2. Here's one region, here's one region. Another example is maybe 3, 1, 5, and stuck. Okay, 3, 1, 5, and oops, 5, 3, 1. I don't know. Right. So this 3, 1, 5 is here. It's this one. It's in this top region over here, and this 5, 1, 3 is in this bottom region right here. And again, these different regions are different leaves. The third and final claim of this proof is that the number of yes leaves in a tree is infactorial. This is true since for an array of n elements, there are infactorial permutations. For example, if you take an array of 3 elements, 1, 2, and 3, there are 6 possible permutations, which is 3 factorial. So with a tree for a given array, we have to account for every possible permutation with every decision we make, or in other words, with every comparison we make. We cut the number of possible leaves in half, leaving us with a runtime of n log n, which proves the initial claim that the lower bound is n log n.